Welcome everybody, this is our video solution to problem 8 from Superquiz 3. A very straightforward problem where we're going to take a triple integral and, well, set it up as a triple iterated integral and then evaluate. So we're given that the domain is just a nice box. So remember when we use this notation here, these x's, they look like time symbols. They actually represent what's called the Cartesian product. So because we have two of these x's, that means there are three sets, and we're going to be looking at triples. We take an x coordinate, a y coordinate, and a z coordinate. The x's go between 0 and 1, the y's between -1 and 1, and the z's between 0 and 2. So by Fubini's theorem, we can actually set up this triple integral as a triple iterated integral, and I can do it in any order I like, and so I'm just going to take the ordering that we have here. So x goes from 0 to 1, y goes from -1 to 1, and z goes from 0 to 2. Then I get to evaluate this triple iterated integral on x, y, z squared, and dv, that will become dx, dy, dz in some order. Okay, well, the z is on the inside, so we start with a dz, then comes a dy, and finally a dx. All right, now, I'll go through the calculation step by step. However, what we should, at least in hindsight, see, but even at the beginning, as we set this up, what we should see is the following. The y is going to go between -1 and 1. So if you think about this as being y times xz squared, then for every value of x and z that you put down, you're going to have a y value which is above 0 and one which is below 0, same distance, right? So if you have like a half for y, you're also going to get -1/2 for y. Which means for every choice of x and z, this product xz squared is going to get multiplied by a positive number and the corresponding negative number. Which, because a triple integral ultimately amounts to a sum, you should expect that everything in this problem is going to cancel out, and your answer should be 0. Right? Always good at the beginning if you know what the answer is going to be. That way, if we go through all of the algebra here and we get something other than 0, then we think maybe we made a mistake. So we expect this to actually equal 0. But let's go through the steps. So we're going to work from the inside out. And actually, you know what we might do is notice like the x, the y, and the z squared are all multiplied together. So in fact, I could even pull the x all the way out and the dx all the way out. And I'll end up with an integral from 0 to 1 of x dx, an integral from -1 to 1 of y dy, and an integral from 0 to 2 of z squared dz. And at this point, we might be best served to actually evaluate this inner integral, this middle one first, because that one's going to end up equaling 0, and it won't matter what the other two are. So this one here, if we anti-differentiate y, we get y squared over 2, y goes from -1 to 1, and this piece then will equal 1/2 minus 1/2, which is 0. Alternatively, you might say, hey, look, y is an odd function. And when you integrate, right, you integrate an odd function from, say, -a to a, right, d, well, whatever we need here, this is always going to equal 0. All right, so without doing all of this work, we might also have, seen that this particular integral was 0. Okay, so it won't really matter what the other two here are because, well, there's a 0 factor.